Well, good morning, everyone. Our second class in this Seeking to Understand the Finite Element Method. As Kepler remarked in his journal as he was making some of his major discoveries on how planets move, he reflected that he was thinking God's very thoughts after him. That was a really exhilarating experience for him, that he made sure to put in his journal. And I believe that's in the field that we're in, we have that opportunity. We have that opportunity to make new discoveries, and it's a exciting ride. It has been that way for me. So why don't we invite God to be part of what we're doing today, and expect that. Heavenly Father, we thank you. We thank you for the privilege of serving you. Almost hard to imagine any greater privilege than being a servant of the Most High God. So we thank you for that calling you've given us. Thank you for this class. Thank you for this university. Thank you for what you're doing here. Thank you for all the faculty and students that are part of it all. We pray that you might be moving and guiding and encouraging and directing, enabling throughout this university, and certainly in our class today. Thank you for the wonders that you've made. Thank you for us to be able to study these things, to imitate them, to learn how to apply these principles in making our world a better place and being your servant. So we commit this time to you. Thank you for your grace to us, your love. In Jesus' name, amen. Okay. Last time we looked at the. I made the comment that the finite element method is just incredibly powerful for understanding the natural world, and it's diverse, can handle a large class of phenomena. And basically, I'm just going to skip through some slides I had last time, and get down to where let's see, here we saw that basically the finite element method is an approach for solving partial differential equations. And I don't know, I don't have a good feel for your undergraduate training, whether actually solving partial differential equations was something you did very much, but that's what the finite element is designed to do. Equations like these up here, and so we're thinking in terms of some variable we're interested in. It can be temperature, in this case, torsion, the flow variable, electric potential. It can be displacement. It can be velocity. Anyway, this type of equations govern those quantities, and the finite element method is designed to be able to capture, to represent these unknown fields in an accurate manner. And so we looked at a little bit of that this finite element method is a subset of what is called the Galerkin method, which does this very same thing, solving a system of partial differential equations for some variable on a spatial domain where boundary conditions are imposed. So you need to treat the boundary as well as the domain itself. So you generally have some idea that either you've got to say, in the case of if this is known as a temperature, you've got some idea what the temperature is on the boundary, or perhaps you've got a heat flux condition on the boundary, and so in that case there's a temperature derivative specified on the boundary. So this is a differential operator. In any case, this Galerkin method is doing the same thing as finite element method does, and we showed that this Galerkin method utilizes what are called test functions, integral of a test function times the basic equation. So it expresses the original equation in what is known as weak form. This weak form that we see here is equivalent to those equations 1 and 2, which are often referred to as the strong form of the equations. But the weak form and strong form are equivalent, and as I tried to say at the end of the last lecture, there's some computational advantages to the weak form. Another very important aspect is that we are this finite element method uses an approximation. You don't have the exact solution, but you're coming up with an approximation of U in terms of some basis functions. I didn't say much about the basis functions. And with the finite element method, it turns out one can use some very, very simple basis functions. Let's just suppose we have some I guess I can use colors here. We have some arbitrary function here, and we want to approximate it with something with a finite number of values. So this thing has values at every point. We want to approximate it, and so we can we can approximate it. We can sample it, say at points here, evenly spaced points, say, and I didn't have to make it this fine, but so if we know what the function is at those points, depending on how fast the function's changing, it's probably good enough for many applications. So how do we approximate in terms of what we've mentioned here? What does that look like? Well, we can use a piecewise linear approximation. In other words, if we have the values at this point, we can just we can just approximate it with a sequence of straight line segments. Okay? And so on. So move the axis up a little bit here. So it turns out that we it's a common choice for these basis functions I'm calling in here are small little what we call tent functions. So if I'm going to project these points here down on the line, and we're going to. I have another scale here. This is 1 and this is 0, and so the basis functions turn out to be what are called, you can use what are called tent functions, piecewise linear functions over a limited domain. These tent functions assume the value 1 at the node and 0 at the neighboring nodes in each case. So it turns out if you weight each of one of these little test functions or basis functions with the right value, in this case AK, you will generate a piecewise linear approximation to the function. So it's common to in the finite element world to refer to these well, as I said up here, I said later in this little discussion is that the thing that distinguishes the finite element method from the more general Galerkin method is that the finite element method uses local basis functions. In other words, each basis function is just restricted to a certain limited portion of the spatial domain. It's non-zero. It's 0 everywhere except for this local region here. So that's what the finite element method is. It uses these local basis functions. So in a 1D situation, you can represent your function, approximate your function in a piecewise linear way with these little. Another term is they're called tent functions because they look like a tent. They're 1 at the node and 0 at the neighboring nodes. Okay, so anyway, it's important to realize what we're doing is an important aspect of the finite element method is working with an approximate solution of this kind. It's in terms of local basis functions. All that clear? Is any questions about this? I don't know if you've been exposed to this before. Okay.
In like linear algebra, we went over some basis functions, but I think that might be a little different. So in this case, when you have a local basis function approximated with a local application at a linear segment that you've approximated across the length of the curve, are you multiplying it by some coefficient to reach the
Yeah.
y value height of the curve, or is it always an amplitude of 1?
No, the function, the basic function itself has an amplitude of 1, maximum amplitude of 1. And for this particular point here, let's just say that this is, let's just say this is 6 here. The a sub k for this function would be 6, and so the function would be the contribution at this point. It would be getting all of its contribution from this series, this sum of basis functions from this basis function. It would be getting 0 from this basis function because this one goes to 0 at the point.
Mm-hmm.
So you can show that summing these kind of functions with appropriate weightings for each one will give you a piecewise approximation to that curve.
So if you were to redraw each of those basis functions with their appropriate weight, would they be drawn much taller? Like
Yes.
that first one would have a height of 6, like
Yes.
a big mountain range
Yes.
that
Yes.
approximates the curve?
Yes.
Okay.
Yes. Yes. Each one would be going up to the curve.
Gotcha.
Yeah.
Almost like a Riemann sum of sorts is what it looks like. Triangular Riemann sum.
Yeah. So anyway, there's a very attractive aspect of this approach is its simplicity, and all right, and so let's go down. I want to highlight another little aspect of what we talked about. And so we showed in this development of the Galerkin method that it's this integral method. We're multiplying by some test functions, and eventually to solve the equation, you end up, your basic solution is a linear system. It's just linear algebra. Some matrix Ik times some vector Ak plus a vector C is 0. It's a standard linear algebra for as far as the mathematics is concerned. These if things are not changing, you can compute these coefficients once, and they're just a property. They're just a property of the domain omega. Okay. And in general, it's the if in many cases this doesn't change, and a sub k is basically dependent on what the right hand side is. In this case, it's been brought over the left hand side. What this c is. Okay.
Okay. What does the AI sub k represent?
This
A sub I k, sorry.
A sub I k is defined right here.
Okay.
It's this integral that involves the basis functions and this differential operator. So you're applying the differential operator to the basis function here, which is typically something simple, doesn't change, and so a lot of the difficulty, a lot of what would appear to be the mathematical complexity and difficulty resides in what generally is a simple integration. Since these are local, even though the integration is over the entire domain, since these are local, these functions are zero over most of the domain. There's only a small region where they're non-zero. So that those integrals are, and if these are piecewise linear or piecewise quadratic, they're simple functions to deal with. So okay, so we I don't know what I did there. Okay. All right. So what distinguishes the Galerkin approach from the more general approach we had before we got to this point is that we use the basis functions for representing our approximate solution U. We use these basis functions as the test functions, as the weighting functions. And so we only have one set of functions in this integral form, or weak form. And then, as I said, we restrict things more and limit our set of functions to these local basis functions. Then the method is referred to as the finite element method. And so what I want to emphasize here, it's not, as far as I can tell, not emphasized like I think it should be in most engineering treatments, is that this method is for solving partial differential equations on a continuum. And so I'm going to encourage that perspective, even though a lot of the exercises we do will have a more of an undergraduate engineering flavor. So we'll get to, probably next time we'll go beyond just the scalar operator. I'm sorry, the scalar unknown to a vector unknown. Okay. And I also said that although there's a wide variety of local operators we could use, there's a restriction, a limitation, in that they need to be smooth enough to support the order of differentiation in the operators D and B. And commonly, the operators D and B, at least in D, have second derivatives. The basis function needs to be able to cope with that. If for example, if this is your basis function, you have a second order derivative. The derivative, the first derivative of this is let's see, maybe, okay, here it's plus, this part is it's plus 1, and then it jumps and is minus 1 for this curve. It's derivative is plus 1 here, minus 1 here. So, and then if you take the next derivative of this, it's 0. It's simply 0. It's a constant and a constant, and then at this discontinuity, it's undefined. So, so you can't take a second derivative of this kind of 10 function. So if this is if that's our operator, differential operator, we've got the second derivatives, we have a problem. And I'm gonna probably more and more start using what's called the Einstein notation, where a repeated subscript means a summation. So that this is a shorthand way of writing this expression right here. I didn't have up this on my previous handout, this part here. I mentioned though integrating by parts can reduce the complexity. If you use the standard formula for integration by parts, which I assume you've been exposed to, and using n sub I as u in the expression we had before for a sub ik. In dv we use this. We can use the integration by parts to get instead an expression for ak of this type here, which has simply first derivatives. So the first derivatives of these two basis functions. And if you're using piecewise linear basis functions, those are well defined. You can perform those integrals. They're simple, actually. These are either 1 or minus 1. These derivatives, and so they're easy to compute. So anyway, and so this is an aspect of important aspect of finite element theory, in that you're able to use very simple basis functions and accurately represent these second order derivatives and represent the physical behavior of the medium in an amazingly accurate way. Okay, I know that's a very brief introduction, brief overview, and it won't be the only time we go over it. I'm going to be referring back to this many times, but just to expose you to it. And I did make a copy. I did make copies to revise that last part of the 4th page that I handed out last week. Okay, so I'm gonna go back. I'm gonna go back to the slides that Dr. Horstmeyer had, and hopefully this will be a little more familiar for you. So he addressed the question: why do we need finite element analysis? Consider a simple structural problem. Let me get my laser pointer. We got this beam. We've got elementary beam theory, which I'm sure you've been exposed to, and we want to deal with see if we apply a given load W at the end of the beam, whether the beam will support it or not. So we want to compute the maximum stress for the structure using simple theory. Is the maximum stress greater than the yield stress? If the answer is no, we can have pretty good confidence that there's gonna be no permanent deformation when you load the beam like this. If it is greater, then plastic deformation has occurred, permanent deformation has occurred. Is the yield stress greater than, what is UTS?
Ultimate strength?
Ultimate tensile strength.
Yeah, ultimate tensile strength. If it's no, then we just, then we only deformed it, permanently deformed it a little bit. However, if the answer is yes, then that the beam breaks, failure occurs. Okay? So this is a very common type of analysis in structural mechanics, and so we're able to we have a formula for computing that, where the stress is equal to W times the length of the beam divided by I, the moment of inertia, given by this formula here. So we can compute. So it's a simple formula for computing whether the stress yields permanent deformation or even failure. Okay, but what happens when we have a more complex version of the same problem? We have a beam like this right here, and the beam has taper, has holes, has a complex cross section, and it's possible that the loading is more complex. Can we still use this formula? It turns out we can't just in a, well, let's just go through it. So we typically have complex structural problems. We make simplifying assumptions. We apply elementary theory as we can. We come up with a preliminary design. We have a safety factor in view, and we end up with a trial solution. If the product needs to be manufactured, we need to produce the design, build a prototype, and perhaps optimize it, test it and optimize it. And we saw that the benefit of the finite element method is that we don't have to iterate this process over and over again of prototyping, testing, and prototyping and testing for many cycles. Instead, we use numerical tools, computer-aided